In this activity, you will learn how the characteristics of the sediment in sedimentary rocks can be clues to their depositional environments. This first slide is going to sound familiar. It's a lot of review from physical geology. And then on the next slide, we'll go and learn a couple new terms and some new inferences that you can draw about the depositional environments of a sedimentary rock. So, this is a grain size chart, and you can see that grain size will vary from pebbles and gravel, so really anything larger than 2 millimeters in diameter of a particle or sediment is considered gravel. And then there are a variety of sizes of sand, ranging from coarse sand to fine sand. And you can also see that there are actually very specific measurements about what the deviations are between a coarse, medium, and fine sand. This is usually something that you would explore more in a sedimentary petrology course or a stratigraphy course, which are normal classes that geology majors take sort of at the 300 level. And by the time you take those courses, you can actually identify just through like visually the difference between a fine and a medium sand. Once you get to particle sizes that are smaller than sand but not quite clay, you get to a particle size known as silt. So silt often feels gritty, and so that can be hard to infer from pictures, but it can be done certainly with a little bit of practice. And clay is the finest particle size. You will not see individual grains when you are looking at clay. For the most part, it will appear like almost like a solid, invisible texture, really. So just no visible particles, really, when you're talking about clay. So in general, we learned in physical geology that as you move further away from a source area, and a source area is usually a mountain, as you move further away from the source area, in general, grain size will decrease. So that makes sense if you think about it. You have a whole bunch of rocks fall off the side of a mountain, and you might have a variety of grain sizes, but you overall will have more large particles there. And as those particles are carried by rivers and wind and water further away from those mountains, those particles will start to break down. And first they'll break into sand, and then they may break down further into silt and clay. It turns out that based on how much wave energy there might be in an environment, that'll also impact the grain size that you're going to see deposited. But in general, you want to think that the smaller the grain size, the larger the distance from that source area or that mountain range. Also, things that you learned about in physical geology are rounding and sorting, and these things typically go hand in hand, where particles and individual grains within a sedimentary rock can be angular in shape, meaning that they have these jagged edges. They can be well rounded, where most of those jagged edges have been rounded off. And then, of course, this is a process where angular particles are carried further away and they bounce along the bottom of rivers, and as that happens, they slowly become more rounded. Until you have these nice well-rounded particles. So in general, as the distance increases, particles tend to go from more angular to more well-rounded. Similarly, when a pile of rocks might fall off of a cliff, you will have a variety of grain sizes, and the grain sizes are referred to as sorting. So when you have a variety of grain sizes, that means that rocks are poorly sorted, meaning that you have a diversity of grain sizes here, from gravel to maybe a sand, and maybe there's some clay you can't see here. But poorly sorted means multiple grain sizes, where well sorted means that all the particles present in the rock, or at least the vast majority of them, are approximately the same diameter, so about the same size. So a new concept in historical geology is the clue that color will tell you in a sedimentary rock. So the color of a sedimentary rock in general will give you some clue as to how much oxygen was present in that environment. So you may see a black rock like a black shale, and black rocks are typically deposited either in deep water or in stagnant water. So stagnant water is going to be like a swamp. A swamp isn't necessarily deep, but the water isn't moving at all. And so because a lot of times the oxygen in water comes from the wind, if the water isn't moving, that oxygen doesn't get really far below the surface in in stagnant water. And so pretty much everything in that water that is below the surface is going to have almost no oxygen in it. The term for an environment with almost no oxygen is called anoxic, and that's because oxic means oxygen and an means none or little. Actually means none. So sometimes you'll see sedimentary rocks that are green to grayish, and those are typically deposited in shallow water, but where there's still some circulation, meaning that there is mixing between the air and the water. And so that mixing is what will incorporate a lot of that oxygen into the water. And when you have a little amount of oxygen, but still some in the water, geologists refer to that as dysoxic, which means little oxygen in the water. So again, that's a characteristic of green and gray rocks. So finally, then we also have red and brown sedimentary rocks. Those are typically deposited on land, and that's what we call a terrestrial deposit. And so on land, there's obviously continuous contact with the air, so that has a lot of oxygen in it, and the word for a lot of oxygen is just oxic. So based on the color of a sedimentary rock, you can determine approximately whether or not there was oxygen or not in that depositional environment. And that tells you a little bit of something about the energy, right? Whether you're talking about stagnant or circulating or on land. The final characteristic we're going to keep in mind when we look at sediment is the maturity of the sediment. And this is something we touched on very briefly if you took my section of physical geology. And that is the idea that sometimes you can have multiple minerals in a rock. One of the things that we learned in physical geology is that as rock and sediment and minerals are transported, that minerals that are unstable will weather, right? And they will weather into minerals that are stable. And we also learned that one of the most stable minerals on Earth is quartz. So what will happen over time is initially when rocks are deposited and sediment is deposited close to the source area, is that it hasn't traveled very far, so there hasn't been a lot of weathering. So you'll have a variety of minerals within the rock. And then as there's further transport, what we start to see is fewer and fewer minerals in those rocks. And then finally, what we have left when a rock has been transported a far distance from the source area is generally only one or two minerals will remain. And this is described as the maturity of the minerals. So rocks that have a variety of minerals in them, like this lithic sandstone you see here, this is considered an immature rock. It is immature because it hasn't developed fully. There's lots of different types of minerals, many of which are not stable in it. As that sediment is transported further, some of those unstable minerals will weather out. Not all of them, but some of them. And that's what we call a submature rock. It is not quite mature yet, but it is on its way. And then when you look at a rock that predominantly has one mineral in it, that is considered a mature rock. So you're going to apply these 5 characteristics, and you're going to look at a variety of samples and determine what all the different characteristics that you can observe in these samples tell you about the depositional environment.